The universe is everything there is, all of space and time, and everything within it. Imagine it as a gigantic bubble that contains all matter and energy, from the tiniest subatomic particles to massive galactic filaments. According to the Big Bang theory, space and time began about 13.8 billion years ago and have been expanding ever since. In the beginning, the universe was incredibly hot and dense, but as it expanded, it cooled down, allowing the first particles and simple atoms to form. These atoms eventually clumped together to form giant clouds of hydrogen and helium, giving birth to the first galaxies and stars. Fast forward to today, and our observable universe is about 93 billion light-years in diameter. That's so vast, it's almost impossible to imagine. But here's something even more mind-blowing. We don't know the full size of the universe. It could be infinite, and we're just seeing a tiny part of it. In ancient times, people believed Earth was the center of everything, but thanks to astronomers like Nicholas Copernicus and Isaac Newton, we learned that Earth is just a small part of the solar system, which itself is a tiny part of the Milky Way galaxy. And the Milky Way, one of hundreds of billions of galaxies in the universe. Now let's talk about dark matter and dark energy. These mysterious substances make up most of the universe. Dark matter, which we can't see directly, accounts for about 25.8% of the universe's mass and energy. Dark energy, even more puzzling, makes up around 69.2%. Ordinary matter, like stars and planets, is just a tiny 4.84%. So what's the fate of the universe? Scientists have a few ideas. Some think it will keep expanding forever, while others believe it might eventually collapse back in on itself. There are even hypotheses about a multiverse, multiple universes existing alongside our own. It's like imagining our universe as just one bubble in a vast cosmic ocean. Now that we've embarked on our cosmic journey, let's take a closer look at the observable universe. According to the general theory of relativity, there are far regions of space that may never interact with ours, even over the entire lifespan of the universe. This is because of the finite speed of light and the continuous expansion of space. Imagine sending a radio message from Earth. Despite our best efforts, it may never reach some regions of space because space itself may be expanding faster than light can travel. The part of the universe we can observe with our telescopes is called the observable universe. This observable region depends on the location of the observer. The proper distance, or the distance as it would be measured at a specific time, including the present, between Earth and the edge of the observable universe is 46 billion light-years. This makes the diameter of the observable universe about 93 billion light-years. However, the distance the light from the edge of the observable universe has traveled is very close to the age of the universe times the speed of light, about 13.8 billion light-years. This doesn't represent the distance at any given time because both the edge of the observable universe and Earth have moved further apart since then. For comparison, the diameter of a typical galaxy is about 30,000 light-years, and the typical distance between two neighboring galaxies is around 3 million light-years. Our Milky Way galaxy is roughly 100,000 to 180,000 light-years in diameter, and our nearest sister galaxy, the Andromeda galaxy, is located about 2.5 million light-years away. Because we cannot observe space beyond the edge of the observable universe, it remains unknown whether the size of the universe in its entirety is finite or infinite. Estimates suggest that if the universe is finite, it must be more than 250 times larger than a Hubble sphere. Some disputed estimates even suggest the total size of the universe, if finite, could be as high as 10 to the power of 10 to the power of 122 megaparsecs. As we continue our journey through the cosmos, let's delve into the age and expansion of the universe. Over time, the universe and its contents have evolved dramatically. For instance, the relative population of quasars and galaxies has fluctuated, and the universe itself has expanded. This expansion is evidenced by the observation that the light from distant galaxies has been redshifted, indicating that these galaxies are moving away from us. Analyses of type Ia supernovae have led to the astonishing conclusion that the universe's expansion is accelerating. The more matter there is in the universe, the stronger the mutual gravitational pull among that matter. If the universe were too dense, it would eventually recollapse into a gravitational singularity. Conversely, if the universe contained too little matter, the self-gravity would be too weak to form astronomical structures like galaxies or planets. Since the Big Bang, the universe has expanded continuously. Remarkably, our universe has just the right mass-energy density, equivalent to about 5 protons per cubic meter, allowing it to expand for the last 13.8 billion years. This has given ample time for the formation of the universe as we observe it today. Dynamical forces acting on the particles within the universe influence the expansion rate. Before 1998, it was widely expected that the expansion rate would be slowing down due to gravitational interactions. This expectation led to the concept of the deceleration parameter, which most cosmologists believed would be positive and related to the matter density of the universe. However, in 1998, 2 independent research groups measured the deceleration parameter and found it to be approximately 8055. This negative value indicates that the second derivative of the cosmic scale factor has been positive for the last 6 billion years, confirming that the expansion rate of the universe is indeed accelerating. As we journey deeper into the cosmic mysteries, we now turn our gaze to the very fabric that weaves the universe together: space-time. Modern physics regards events as being organized into space-time. This revolutionary idea originated with the special theory of relativity, which predicts that if one observer sees 2 events happening in different places at the same time, a second observer who is moving relative to the first will see those events happening at different times. The 2 observers will disagree on the time between the events, and they will disagree about the distance separating the events. But they will agree on the speed of light, and they will measure the same value for the combination. The square root of the absolute value of this quantity is called the interval between the 2 events. The interval expresses how widely separated events are, not just in space or in time, but in the combined setting of space-time. Yet the special theory of relativity cannot account for gravity. Its successor, the general theory of relativity, explains gravity by recognizing that space-time is not fixed, but instead dynamical. In general relativity, gravitational force is reimagined as curvature of space-time. A curved path like an orbit is not the result of a force deflecting a body from an ideal straight-line path, but rather the body's attempt to fall freely through a background that is itself curved by the presence of other masses. A remark by physicist John Archibald Wheeler has become proverbial among those who study the cosmos. Space-time tells matter how to move. Matter tells space-time how to curve. Therefore, there is no point in considering one without the other. The Newtonian theory of gravity is a good approximation to the predictions of general relativity when gravitational effects are weak and objects are moving slowly compared to the speed of light. The relationship between matter distribution and space-time curvature is given by the Einstein field equations, which require tensor calculus to express. The solutions to these equations include not only the space-time of special relativity, known as Minkowski space-time, but also Schwarzschild spacetimes, which describe black holes, FLRW space-time, which describes an expanding universe, and more. The universe appears to be a smooth space-time continuum consisting of 3 spatial dimensions and 1 temporal dimension. Thus, an event in the space-time of the physical universe can be identified by a set of 4 coordinates, x, y, z, t. On average, space is observed to be very nearly flat, meaning that Euclidean geometry is empirically true with high accuracy throughout most of the universe. Space-time also appears to have a simply connected topology, similar to a sphere, at least on the length scale of the observable universe. However, present observations cannot exclude the possibilities that the universe has more dimensions, as postulated by theories such as string theory, and that its space-time may have a multiply connected global topology, analogous to the cylindrical or toroidal topologies of 2-dimensional spaces. General relativity describes how space-time is curved and bent by mass and energy, a phenomenon we perceive as gravity. But what about the larger shape of the universe? This brings us to the intriguing concepts of local and global geometry. In cosmology, scientists often work with a given space-like slice of space-time called co-moving coordinates. These coordinates help us understand the universe's geometry from a specific point of view. Imagine looking back in time to the very edge of what we can observe, the backward light cone. This cone defines the cosmological horizon, the boundary between the observable and the unobservable regions of the universe. The cosmological horizon, also known as the particle horizon or the light horizon, marks the maximum distance from which particles can have traveled to reach us within the age of the universe. This horizon is a fundamental limit, shaped by the universe's expansion and its age. The nature of the cosmological horizon varies depending on the cosmological model. One crucial parameter in these models is the density parameter, omega. This parameter determines the universe's future evolution and selects one of three possible geometries: flat, open, or closed, depending on whether omega is equal to, less than, or greater than 1. Observations from missions like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided us with detailed maps of the cosmic microwave background, CMB. These maps suggest that the universe is infinite in extent, but has a finite age. This aligns with the Friedmann-Lemaitre-Robertson-Walker FLRW models, which describe an expanding, flat, homogeneous universe dominated by dark matter and dark energy. These FLRW models also support the theory of cosmic inflation, a rapid expansion that occurred in the universe's earliest moments. This inflationary model explains many of the observed features of the universe, including its large-scale uniformity and the slight variations in the CMB. As we ponder the shape of the universe, we are reminded of another profound question. Why does the universe support life as we know it? This brings us to the fine-tuned universe hypothesis. The fine-tuned universe hypothesis is the proposition that the conditions that allow the existence of observable life in the universe can only occur when certain universal fundamental physical constants lie within a very narrow range of values. Imagine the universe as a grand cosmic symphony, where each note must be perfectly in tune for life to flourish. According to this hypothesis, if any of several fundamental constants were only slightly different, the universe would have been unlikely to be conducive to the establishment and development of matter, astronomical structures, elemental diversity, or life as it is understood. The balance is so delicate that even the smallest deviation could mean the difference between a universe teeming with life and a lifeless void. Whether this is true, and whether that question is even logically meaningful to ask, are subjects of much debate. The proposition is discussed among philosophers, scientists, theologians, and proponents of creationism. Some view it as evidence of a purposeful design, while others see it as a natural consequence of the laws of physics. Regardless of where you stand on this debate, the fine-tuned universe hypothesis invites us to marvel at the intricate dance of cosmic forces that make our existence possible. It challenges us to explore the deep connections between the fundamental constants of nature and the emergence of life.